Okay, thank you very much. Shall I start? Thank you very much. At the outset, I would like to thank the Government of AP and the Ministry of Higher Education, Honorable Vice Chancellor of JNTU Kakinada. Systems is comprised of random process, analog communication, and digital communication. The highlighted part, which is with the red, the analog communication part, I was asked to present. I will stick to the analog communication part. Amplitude modulation and demodulation, angle modulation and demodulation, spectra of AM and FM, superheated and receiver, circuits of analog communication, information theory and entropy, mutual information channel capacity. In addition, signal analysis is very much required. So therefore, I'll start my today's class with an emphasis to signal analysis. I will start the class with signal analysis. This is a detailed analysis of GATE 2020 Electronics and Communication Engineering paper. Coming to the communication systems part, we obtained about 10.6% of weightage in communication systems engineering. So the prerequisites for analog communication is signal systems. So analog communication and digital communication combinedly, we can consider it as a communication which we have to take up the examination in GATE. So apart from the analog and digital communication, signal systems is also required for digital signal processing and subjects like digital image processing. This is my detailed presentation overview of the entire analog communication study. My presentation outline each session, I was allocated with 12 sessions. Each day, starting from today up to 6th of next month, that is July 6th, I will be presenting my lectures from 3 p.m. to 5 p.m. In my first lecture today, I will try to introduce the signals to the audience, and at the same time, the Fourier analysis of signals comprises of Fourier series and Fourier transforms. In addition to Fourier series and Fourier transform, I will also explain about Hilbert transform, that is very much required for the generation of suppressed carrier modulated signals like single sideband modulation. Few worked out examples and the earlier gate problems also we will discuss in this class. So in my second class, I will discuss about the CW modulation. CW stands for continuous wave modulation, comprised of full carrier AM, that is conventional, we also call it as conventional AM, and its time domain representation, the frequency domain spectra, the power relations, the current relations, and few problems on the conventional AM, that is AM full carrier. In the third class, I will discuss with the suppressed carrier modulation mechanisms under the same heading of CW modulation, in which the suppressed carrier modulation mechanism like double sideband suppressed carrier, single sideband suppressed carrier, vestigial sideband modulation and their applications of all forms of AM, that is including the full carrier AM and the 3 suppressed carrier AMs, their generation, their detection and their applications, a comparative analysis and few problems also on gate model we will discuss in the third class. In my fourth class, this is my presentation plan, so therefore it is very much essential for me to present a brief. In the same CW modulation heading, there is another concept called angle modulation. Under angle modulation, we need to discuss about frequency modulation and phase modulation. The frequency modulation may be again divided into two, that is narrowband frequency modulation and wideband frequency modulation with some problems. The bandwidth representation, the spectral representation, certain special functions like Bessel functions we will use in the generation of wideband FM signal. That also I will discuss in the fourth class. In the fifth class, how can we generate the next form of angle modulated signal, that is the phase modulated signal, and the comparison in between FM and PM, the generations and the entire detection part of the angle modulated systems we will discuss in the fifth class in addition to problems. In the sixth class, it is wise to connect the AM and FM transmitters as well receivers soon after the completion of conventional modulation mechanism like analog modulation mechanisms like AM, FM, and PM. So therefore, AM transmitters and receivers, FM transmitters and receivers will be discussed in the 6th class. In the 7th class, I will discuss with exclusively the receivers part. The whatever the leftover part in receivers, I will discuss with problems. In 6th class, based on time, allocated time, I will discuss few problems. And in the 7th class, exclusively the problems on recent gate examinations and relevant problems pertaining to the AM and FM transmitters and receivers will be discussed. 8th class, completely allocated to the noise and the modeling of noise, several different noise distributions, how to calculate noise figure, how to calculate noise temperatures, and all that, the distributions of the entire noise part, which is useful for the entire communication study, for analog communication as well to the next part of communication, the digital communication part also I will discuss in the 8th class. In the 9th class, I will start with the noise part, especially in the continuous wave modulation mechanisms. As I told you earlier, the full carrier AM, the 3 suppressed carrier AMs, namely the DSBS AM, SSB AM, and VSB AM, and the performance in the presence of noise, their noise performance will be calculated. A bit mathematically involved concepts are being discussed. And in addition to the amplitude modulation mechanisms and its 4 variants, I'll also discuss the analog modulation mechanisms like angle modulation mechanisms. They are the FM and PM, and their noise calculations also I'll discuss. And in my 10th class, in the 10th class, I'll discuss about sampling, the different sampling techniques, the low pass sampling theorem, the band pass sampling theorem, the Nyquist rate problems, and all that I'll discuss in my 10th class. In my 11th class, I'll discuss about the pulse analog modulation mechanisms on converting an analog signal by using some sampling techniques. A signal can be represented as a pulse analog modulated signal, and its variants like pulse amplitude modulation, pulse width modulation, and pulse position modulation we will discuss in the 11th class, and a few problems relevant to the gate examination also we will discuss. In my last class, I'll try to address the information theory and coding part of the information theory, like how do you measure the information, like entropy, the measure of information, we call it as entropy, and mutual information and self information, several different coding techniques like Hoffman coding, Shannon-Fano coding. This is what is my entire presentation overview, which covers the entire analog communication study. With these 12 classes, I think I can cover the entire analog communication part quite satisfactorily. Now come to the today's class. This is my presentation outline. I'll try to start with the introduction to signals and the continuous domain and discrete time, continuous time and discrete time signals I'll discuss. And later I'll discuss about the singularity functions, the Fourier series, followed by few problems on Fourier series, the Fourier transform for representing aperiodic signals, few problems on Fourier transform, especially the cosinusoid and sinusoid signals, how to perform the Fourier transform of those signals. Especially we use them for modulation. So therefore, I feel like discussing about those 2 signals, especially in the Fourier transform part, and the remaining transform that we require mostly is Hilbert transform for obtaining an SSB signal, not only for us obtaining SSB signal, for the generation of the band pass signals also we need often to convert a signal by 90 degrees. So therefore Hilbert transform serves the purpose of field in a room as a signal like this. Similarly, a signal with varying dimensions like an RGB signal, which is a signal whose picture can easily be seen, which is an image. It varies with dimensions. A speech, an electromagnetic field in a room, or an image can also be taken as an examples for signals. There are signals which we basically classify them into number of independent variables with which they are associated actually. If a signal is a function of only one variable, we call it as a one-dimensional signal. If for example, you can see the speech signal, which is a human speech, which can be considered as a one-dimensional signal, or an AC power which is supplied from the machine, an AC power supply, we can say that it is variable of time and the amplitude varies with time. Similarly, the electrocardiograph of a human being can also be considered as an example for a one-dimensional signal. So therefore, whatever may be the dimension, the independent and dependent variables plays vital role. Another example is similarly, if a signal is a function of two or more variables, it is said to be a multidimensional signal, or if a signal is a function of two variables, it is said to be a two-dimensional signal. For example, a picture you can see whose dimensionality can be seen here. The S of xy you can see here. The S of xy, what we can say that if S of xy is an image, I can say that the x comma y is the location, that is the x and y location, and the intensity at this location, you can see a dark intensity is present here, a white intensity is being present here. So therefore it is an example of two-dimensional signal. The other name to picture is image. So a picture or an X-ray image which is shown here, or a sonogram, the fetus can be seen by an electronic sonogram picture, which is also can be considered as an example of a two-dimensional signal. So the moving picture, the third dimension, the three-dimensional signal can be considered as a video where you can see x, y, and t are the three dimensions of this particular signal, where we can clearly say that it is an example of 3D. We can clearly see what is an example of a one-dimensional signal, a two-dimensional signal, and a three-dimensional signal. We need to model after the study. We are supposed to properly model the signal. The representation of a signal by a mathematical expression is known as a signal modeling. Let us suppose an electrical signal you can see from power supply, which is in here. X of t is yes. If you record it, it will be a continuous time signal. So this is the general representation of the continuous time signal. The x-axis is t and the y-axis x of t. So therefore, a function of t is the 1D signal, we can say, are a best example of a continuous time signal. A discrete time signal, unlike a continuous time signal, is not a continuous signal. If the same signal is being sampled at a uniform interval of time, then I can get infinitesimal sample amplitude here. In the next interval, I will get a sample amplitude here. In the next interval, I will get a sample amplitude. If these sample amplitudes or instants are being represented as a signal, then we can come out with this kind of representation. Now x of t takes the new form of x of nts for n varying from minus infinity to infinity, whereas here n varying from minus 3 to 3. This signal x of n can be considered as a best example of a discrete time signal. The discrete time signals are generally defined at a discrete instance of time, and it is represented as x of n. So when Ts is called as the sampling period, I can represent the same analog signal where x of t, which is sampled at uniform intervals of time, obtaining a discrete time signal from a continuous time signal, which is represented here. On sampling, we can come out with a discrete time signal. The sample amplitude are being represented at an interval of Ts. We call it as a sampling period, and n is an integer ranging from minus, here n is from minus 3 to 3. So x of n is now a sampled version of a continuous time signal x of t. So therefore, on sampling by a pulse train, let us suppose x of nts may be a discrete time signal. This is how we try to convert the continuous time signal into discrete time, and this is what is the representation of continuous time signals and discrete times. In addition to the continuous time and the discrete time, we also have a digital signal in which we have a digital signal in which we can represent the amplitude in discrete domain and time also in discrete domain. Prior to that, we'll now clearly discuss. You can see here, I'll take out the laser pointer instead. You can see here, this is a continuous time signal in which the amplitude of the signal is continuously varying. You can see here. As well, the time is also continuously varying. So therefore, I can conclude that the amplitude of the signal is continuous, as well the time of the signal x of t is also continuous. So therefore, we can classify this as a clear example for a continuous time signal or an analog signal. So therefore, an analog continuous time signal is continuous in its amplitude and continuous in its time. This is the representation of a continuous time analog signal or continuous time signal. Just on the next category or next classification, we can have the discrete time signals in which if the analog signal is being sampled at a rate Ts with a sample period Ts, then the instant amplitudes where my sample period Ts happen, the instantaneous amplitude is being taken, and then it is represented. It is representing the signal with the number of samples on this axis and their amplitudes x of n on this axis, which is being their strength, I can say. If so, therefore, the amplitude you can have continuous variation of the amplitudes at discrete intervals of time. You can clearly see. So therefore, this is a signal which we can call it as a discrete time signal in which the amplitude of the signal is though continuous, but the time is represented in discrete. So on the third categorization, a pure digital signal in which we can say, you can see here is a digital signal in which the amplitude is discrete at discrete amplitudes as well discrete times. You can also see. So this is the three categorizations of continuous time signals: the discrete time signal and a digital signal. So in a digital signal, you need to have ones and zeros. So to complete this part, I have included the processors also. We have two kinds of processors: an analog signal processor and a digital signal processor. To perform operations on the either a continuous data or a discrete time data or a digital data, we need to develop processors which performs operations on the data according to a programmed instructions. On the left hand part of the slide, you can see here is an analog signal processor in which it takes analog input signal as its input, and on processing by an analog signal processor will get an analog output signal. Opposite to that, we have a digital signal processor in which you can see two functional blocks are additionally being additionally being added at this location and at this location to the analog signal processing unit, in which we need to convert the analog signal by using an analog to digital converter. Then the digital outcome analog is input signal, analog input signal it will take, and it will convert into the digital output. That digital output is input to the digital signal processor. The digital input it will take and it will process and generates again a digital output. But to the outside world, we need to represent the signal in analog form, in its original form. We need to represent. So therefore, again, an inverse process to be carried out by using a DTA, digital to analog converter, and after that will come out with the processed signal using a digital signal processor. Here we processed the signal using an analog signal processor. So these two processes, we can say that an analog signal processing and a digital signal processing. Analog signal processing doesn't comprise of A to D and D to A. A digital signal processor comprises of A to D and D to A prior to and after the signal processing. The signal processing carried out in analog part is analog signal processing, and digital part is a digital signal processing. Now we will move on to the real-time examples of analog signal recording and the corresponding digital signal recording. Let us suppose an analog audio signal is being taken and recorded here by the direction of the tape traveling and will the head movement and writer head, how the head is reading the information, analog information, and after that it is being generating it as analog output through the loudspeaker. This is the way of recording direction of the tape travel also. You can see, observe here from the slide. It's an analog signal recording. Similar digital signal recording is like taking an analog signal and converting, as we have seen in the earlier slide, the ATD conversion process followed by a digital signal process, and then DPA. The same is can be observed here. Signal is converted into numbers, that is an analog signal is converted into the numbers that can be understandable by the machine, which we call it as a digital computer, and it will generate, it processes the signal, and then the numbers are then converted into the signals that can be capable of delivered through again analog device like a loud. Same, the analog signal and input and analog signal output, these two units are same. Only thing is it is an analog process, whereas this is a digital process. An example of certain properties of the impulse function also we can see here. X of t delta t is equal to x of 0 delta t, and the second property is x of t delta t minus t naught is x of t naught delta t minus t naught, delta some constant alpha times t minus beta is equal to 1 by alpha delta t minus beta. The fourth property is, or the entire minus infinity to infinity, the integration over the any delta function will be 1, and integral minus infinity to infinity x of t delta t minus tau is x of t naught. X of t convolved with delta t minus t naught is x of t minus t naught. These are few properties of the impulse function. Coming to the Fourier series next, so there are several different classes of signals. I am not discussing all the classes of signals like deterministic and random signals, power and energy signals. So many class categorizations are there, but as the time is limited, we are allocated with only a few number of classes. We need to quickly go through the Fourier's analysis. Fourier has represented the signals that can be represented as a sum of periodic signals. Every periodic signal could be represented as a sum of sinusoid is the Fourier series postulation. The representation of a function or a signal f of t over an interval 0 to t by a linear combination of set of infinite number of mutually orthogonal functions, which we call it as a Fourier series representation. For the existence of Fourier series, the Dirichlet conditions must be satisfied. As we all know, Fourier series exists for the existence of Fourier series. We divide the entire Fourier analysis into two categorizations: trigonometric Fourier series into two categories: trigonometric Fourier series and exponential Fourier series. He is the man who invented the Fourier analysis. The three Dirichlet conditions, you can see the function f of t, where we want to represent it as a function of sines and cosines, should be absolutely integrable over the interval t, that is integral minus t by 2 to t by 2 mod f of t dt should be less than infinite. The second Dirichlet condition states that the function f of t must have finite number of discontinuities, and the third Dirichlet condition states that the function f of t must remain finite and must have only finite number of maxima and minima. That is, absolute integrability should be the first property. We call it as the weak Dirichlet conditions. The other two Dirichlet conditions, we generally call them as strong Dirichlet conditions, in which the function should have finite number of discontinuities and finite number of maxima and minima. These three Dirichlet conditions are satisfied, then we can go for the computation of Fourier series. Trigonometric Fourier series representation means the representation of a function over an interval 0 to t by a linear combination of infinite number of trigonometric functions. We can have cos n omega t and sin n omega t. This is how we can represent f of t equal to a naught cos 0 omega naught t, a1 cos 1 omega naught t, a2 cos 2 omega naught t, an cos n omega naught t, and so on. Similarly, plus b naught sin 0 omega naught t, b1 sin 1 omega naught t, b2 sin 2 omega naught t, and so on. Bn sin n omega naught t. So therefore, as we can say that this is what is the next step formulation, where generally the trigonometric Fourier series may be represented as f of t is equal to a naught plus sigma n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t is the standard representation of trigonometric Fourier series, in which we now see what is this a naught in the trigonometric Fourier series representation of a naught plus sigma n equal to 1 to infinity n cos n omega naught t plus bn sin n omega naught t. We can say that a naught is the average value of the signal component of f of t at the origin. The clear definition of that is 1 by t integral t naught to t naught plus t f of t dt can be used for the computation of the average value of the signal, which is the component of the function at the origin. It is a DC value. The second one, an, the component of the function f of t along cos n omega naught t. N omega naught is the suffix which represents the even component, which can be defined as, mathematically represented as, an 2 by t integral t naught to t naught plus t f of t cos n omega naught t dt. Similarly, the odd function or the odd component also, bn, can be computed. It is the odd component of f sin n omega naught t dt. bn is 2 by t. I need to correct it to omega naught. This is not omega 0. Here also it is omega naught. So bn 2 by t integral t naught to t naught plus t f of t sin n omega naught t. F of t cos n omega naught t is an, sin n omega naught t is bn, 1 by t, which is the average value of the signal, which is a DC component. This is the trigonometric Fourier series representation. Similarly, the exponential Fourier series also can be represented like this. Exponential Fourier series often we use for the generation of, you can please make a note of it, exponential Fourier series can be utilized for the generation of an angle modulated signal, especially a wideband FM signal, an narrowband FM signal, which is quite similar to that of AM in terms of power and bandwidth, whereas a wideband FM signal, we can't generate a wideband FM signal without the use of the exponential Fourier series. The exponential Fourier series is quite useful for us for the generation of wideband frequency modulated signals. Exponential Fourier series representation means a representation of the function over the interval 0 to t by a linear combination of infinite number of exponentials. The final representation of this is f of t is equal to e power j n omega naught t, can be represented as a sum of c naught plus sigma n equal to 1 to infinity cn e power j n omega naught t plus sigma n equal to 1 to infinity c minus n, c of minus n e power minus j n omega naught t. So with the changing of the limits, we can also differently, if you want to represent it as e power j n omega naught t, then n takes on minus 1 to minus infinity. That is the only change. You can note it. Here f of t is equal to sigma n equal to minus infinity to infinity cn e power j n omega naught t, right? So this is what is the exponential Fourier series. Here also we can compute c naught, which is the component. Again, it is a DC value similar to a naught, 1 by t integral t naught to t naught plus t f of t dt is the mathematical formulation to compute the c naught value, which is average in the exponential Fourier series. Component of f of t along e power j n omega naught t is cn, which can be computed by 1 by t integral t naught to t naught plus t f of t power minus j n omega naught t dt. Similarly, c of minus n can be a component of f of t along e power minus j n omega naught t, which we can compute by using this formulation. So the relation between, we have seen two forms of Fourier series, the trigonometric Fourier series and the exponential Fourier series. We can relate them. We can relate the trigonometric Fourier series with the exponential Fourier series. The trigonometric Fourier series to exponential Fourier series coefficients in terms of trigonometric Fourier series, that is C naught, Cn and C minus n are the exponential Fourier series coefficients that can be obtained in terms of the trigonometric Fourier series, like C naught equal to A naught, Cn equal to An minus j Bn by 2, C minus n is equal to An plus j Bn by 2. Similarly, the trigonometric Fourier series coefficients can also be obtained in terms of the exponential Fourier series. The A naught, An and Bn can be obtained in terms of the exponential Fourier series coefficients. They are A naught equal to C naught, An equal to Cn plus C minus n, and Bn equal to j of Cn minus C minus n. Coming to the convergence of Fourier series, as I told you earlier, the absolute integrability is called as the weak Dirichlet condition. Generally, people in some books it is being represented like this. The other two Dirichlet conditions, like function should have finite number of maxima and minima and a finite number of discontinuities, are generally known as two strong Dirichlet conditions. On the satisfactory Dirichlet conditions, we can compute for we can proceed for the computation of Fourier series. Other important points one can note down on Fourier series. If a function is even, then the corresponding Fourier series contains only even components, and odd components will not be obtained, will be 0. If the function is even, then the corresponding Fourier series contains only even components. Similarly, if a function is odd, so therefore for an even function we'll get even components. For an odd function, its Fourier series representation doesn't contain any even components, it contains only odd components. So therefore, for an even function, if you compute the Fourier series, you will come out with even components. For an odd function, you will come out with odd components. If a function exhibits a hidden symmetry, then the corresponding Fourier series contains either even component or odd component. Why? Because the kind of symmetry that the function exhibits is a hidden symmetry. So therefore, the Fourier series contains either even or odd components. If a function exhibits a rotational or half-wave symmetry, then the corresponding Fourier series contains only odd harmonics, both even and odd. Only Fourier series contains odd harmonics, both even harmonics or odd harmonics can be obtained. So those are other findings of the Fourier series. The spectrum of a continuous time Fourier series, that is CTFS, you can say, the spectrum of a continuous time Fourier series can be x of t or f of t, continuous time and then periodic. The Fourier series, whose Fourier series, the periodic continuous signal, whose Fourier series again will be a discrete one. Key point: Fourier series is applicable for periodic signals. Fourier series always generate discrete spectrum, and if it is a continuous time one, then the spectrum becomes a periodic. If the input signal is continuous time, the third point, then the spectrum always a periodic. Again, I'll repeat it. Fourier series is applicable only for periodic signals. Fourier series always generates a discrete spectrum. If the input signal is continuous, then the spectrum always a periodic. Few problems also we will now discuss. Please note down. This question has come in the recent 2011 GATE examination for 1 mark. The trigonometric Fourier series of an even function of time does not have A, the DC term, B, the cosine term, C, the sine term, D, the odd terms. We have seen in the key points that the solution is like for a periodic even function, the trigonometric Fourier series does not contain the sine terms, which is odd functions. Why? Because even function consists of even terms, we have seen in the previous slide. So therefore it contains the it doesn't contain the sine terms, that is odd function. It has DC term and cosine terms of all harmonics. So therefore, for a periodic even function, the trigonometric Fourier series does not contain the sine terms. So therefore, what it does not contain is the question. So therefore, the answer is C. Sine terms it does not contain. We'll move on to the next problem. Note down the trigonometric Fourier series of a periodic time function can have only A. Cosine terms, B. Sine terms, C. Cosine and sine terms, D. DC and cosine terms. The solution is that we know that the representation of trigonometric Fourier series x of t a naught plus sigma n equal 0 to infinity n cos n omega naught t plus sigma n equal to 1 to infinity n sin n omega. The series has cosine terms of all harmonics n omega naught can have 0, 1, 2, 3 with 0th harmonic is the DC term, the average or mean value is a naught, and sine terms of all harmonics n omega naught will be 1 to with n takes on any integer value 1 to infinity. So therefore, it will consist of the cosine and the sine. Trigonometric Fourier series of a periodic time function can only have the cosine and sine terms is the answer. So therefore, the DC term, the where 0th harmonic is the DC term, so it doesn't consist of that. Sine and cosine terms, the Fourier series of a periodic time. The third question. Note down. The Fourier series of an odd periodic function contains the it is given in gate 94 examination for 1 mark. Odd harmonics, even harmonics, the cosine terms, the sine term. We know that if a periodic function is odd, the DC term is 0, and also the cosine term, the even symmetry exhibits, it contains only the sine term. So D is the ultimate answer. For odd periodic functions, it consists of sine terms. The previous question you can see. For a periodic time function can only have the sine and cosine terms. The first question is the trigonometric Fourier series of an even function of time does not have the sine terms. So the fourth problem, we will move on to the fourth problem. For the Fourier series of a real periodic function has P cosine terms if it is even, Q sine terms if it is even, R cosine terms if it is odd, sine terms if it is odd. Which of the above statements are correct is given in 2009. So therefore we have P and S means cosine terms if if it is even, the solution is the Fourier series for a real periodic function which should have only cosine terms if it is even and sine terms if it is odd. So therefore, A comprises of the answer which comprises of P and S. Cosine terms if it is even, sine terms if it is odd. It's a simple question. The next question is, which of the following cannot be the Fourier series expansion of a periodic signal? X of t equal to 2 cos t plus 3 cos 3t. X of t is equal to 2 cos pi t plus 7 cos t. X of t is equal to cos t plus 0.5, and D for the space constant, it is written here x of t 2 cos 1.5 pi t plus sin 3.5 t. It is given in 2002 GATE examination. The solution to this is x of t, the function which is for all the four we have done and come out with the answer. We can have x of t 2 cos t plus 3 cos t is a periodic signal with fundamental omega not equal to 1. X of t is 2 cos pi t plus 7, which is second one, is aperiodic or non-periodic. Okay, so for a continuous time for periodic signals only we need to compute. X of t is a periodic function, the C1 cos t plus 0.5 is a periodic signal. Okay, so D x of t 2 cos 1.5 t plus 3.5 t, first term has frequency 1.5 pi, second term has a frequency of 3.5 pi. So therefore this is again so about the ratio also we can have a rational number which is again periodic. A x of t 2 cos t plus 3 cos 3t is a periodic signal with a fundamental period we obtain. Similarly, for the second one, we cannot is not a rational number. We have not obtained a rational number as the period. So therefore, it is not the frequency term. Omega 2 and omega 1. We have got a periodic result. So therefore, the second signal is not periodic, whereas the first, third, and fourth signal. So the rational number is a periodic signal with the fundamental frequency 0.5 pi. Since D is non-periodic, so does not satisfy the Dirichlet condition and cannot be expanded in Fourier series. So therefore, the answer is B. So the next problem, choose the function f of t minus infinity less than t less than infinity for which a Fourier series cannot be defined. For the signal 3 sin 25 pi t, 4 cos 20 t plus 3 plus 2 sin 710 t, e power minus mod t sin 25 t and 1. It is given in 2005 GATE examination for 1 mark. The solution for this is the Fourier series is defined for a periodic function and a constant. So therefore, for A, it is periodic with omega is cannot is the requirement. So therefore, it is periodic. The second function is also a periodic function. The fourth one is a constant. So Fourier series exists a DC quantity. So the third one, e power minus t sin 25t due to decaying exponential. Decaying function is not periodic, so Fourier series cannot be defined for it. So therefore, C is the answer. The next problem and the corresponding solution also is being displayed here. The Fourier series expansion of a real periodic signal with fundamental frequency is given by f naught, and the periodic signal gp of t sigma n equal to minus infinity infinity cn e power j 2 pi n f naught t. It is given that C3 is 3 plus 5j, then C minus 3 is, C3 is given, we can calculate the real, we know that the real periodic signal C of minus k is C of k, so therefore C of minus 3 is C of 3 star. So therefore, it's a complex conjugate 3 minus j is the answer. So we got 3 minus j as the fourth option. So therefore 3 minus j, this star should be printed here. Okay, C of minus k is ck star, which is the complex conjugate of 3 minus j5 is 3 plus j5 is 3 minus j5. So okay, we deal with the periodic signals using Fourier series. How to deal with now the aperiodic signals that are shown here, which is an example of an aperiodic signal. If t tends to infinity, what will happen is the question. So therefore, if t tends to infinity, we need to concentrate on the analysis of aperiodic signals. Fourier also proposed another representation for dealing with an aperiodic kind of signals, like the Fourier representation, new representation is called as Fourier transform. The magnitude spectrum of an aperiodic signal is not a line spectrum, we know, as with a periodic signal, but instead it occupies a continuum of frequencies. To overcome the shortcoming, Fourier has developed a mathematical model to transform the signals between time or spatial domain into a new representation in frequency domain. We can see the spectral representation of signal in Fourier transform domain. Generally, we call it as Fourier transform, which we call it as Fourier transform. This Fourier transform has a numerous number of applications in engineering and physics. We use it in LTI systems, the radar systems, the astronomy, and in signal processing, speech processing, image processing, and in video processing, we use the Fourier transform. The analysis represent our analysis equation of Fourier transform. You can see here f of omega, capital F of omega is equal, it's a continuous CFT, continuous Fourier transform, integral minus infinity to infinity. F of t, a function f of t is to be Fourier transformed. Here also the three Dirichlet conditions need to be satisfied. On satisfactory of Dirichlet conditions, one can go for the computation of Fourier transform. F of t power minus j omega t dt, it is in continuous domain minus infinity to infinity. This equation we call it as analysis equation. The inverse Fourier transform is also a possibility. F of t is equal to 1 by 2 pi integral minus infinity to infinity f of omega e power j omega t d omega. This e power minus j omega t here in the forward Fourier transform, I call it as forward Fourier transform, and this is inverse Fourier transform. So therefore forward in the Fourier transform representation, whatever the function with which we are multiplying this exponentiation is called as the kernel or mother. It is otherwise called as basis function. So therefore the basis function to Fourier is e power minus j omega t or plus j omega t. This minus j omega t can be used here and plus j omega t can be used here. Both can be interchanged. So this inverse Fourier transform equation can be generally referred to as synthesis equation, and the forward Fourier transform equation is referred as the analysis equation. So in turn, the f of omega and f of t can be called as Fourier transform pair. So we forget to note that this omega, the new parameter that we have defined now, is equal to 2 pi of the angular frequency. Here also for the existence of Fourier transform, absolute integrability of the function, finite number of discontinuities at finite interval, and a finite number of maxima minima conditions proposed by Dirichlet need to be satisfied. So the spectrum of continuous Fourier transform, we can see for a signal which is aperiodic, if I compute my Fourier transform for an aperiodic signal, and the spectrum is continuous and aperiodic, so therefore we need to take this as a key point. Fourier transform is applicable only for aperiodic, and Fourier transform always generate a continuous spectrum. Please note it. Fourier transform always generates why? Because it's a continuous Fourier transform where we have computed the Fourier transform from minus infinity to infinity. In continuous time, we'll get a continuous spectrum, which in continuous time will get an aperiodic spectral representation. The third point here also to be noted, if the input signal is a continuous time, then the spectrum always aperiodic. Spectrum will always be aperiodic. So the key points to be noted is Fourier transform is applicable only for aperiodic signals. Fourier transform always generates continuous spectrum. If the input signal is in continuous time, then the spectrum is always aperiodic. Coming to the property quickly, I'll go through to refresh the Fourier analysis, which is very much essential for the analog communication study. I feel that the Fourier analysis need to be covered first. We'll do a few numericals on a cosinusoid and a sinusoid after quickly completing the properties of Fourier transform. The linearity a1 f1 of t plus a2 f2 of t is a1 f1 of omega, capital F1 of omega plus a2 f2. This property is linearity. The time reversal f of minus t, Fourier transform f of minus omega. The time scaling property f of at is 1 by a, f of omega by a is the time scale. Significance of scaling property is very important for us. So you can see, okay, compare to look at these two representations in spatial or time domain and in spectral domain. Okay, time compression of a signal results in spectral expansion. Time expansion of the signal results in spectral compression. So therefore, if you see these two signals, I can say that this is a compressed time signal. This is an expanded time signal. A compressed time signal's Fourier transform looks a bit expanded. So therefore, spectral expansion can be seen in time compressed signal. Comparatively, I am just speaking. If you compare these two spectrums and these two time domain signals, when compared to this is expanded. When compared to this is compressed. So a compressed signal can be seen here, an expanded signal in time domain or spatial domain can be seen here. Similarly, whose Fourier transform is expanded when compared to the Fourier transform of the corresponding expanded signal. So therefore, time compression of a signal results in spectral expansion. The time expansion of a signal results in spectral compression. So the spectrum looks compressed when compared to this. Why? Because the signal is compressed. So we make use of the time scaling property quite often in communication, also in signal processing. The next property of Fourier transform is time shifting. You can see the time shifting property here. F of t minus t naught is f of omega e power j t omega t naught. It's an even function. This time shifted pulse is both even and odd. This is the time shifted pulse, and this is an even function whose Fourier transform can be seen here. And the shifted functions Fourier transform can be observed here. Time shifted pulse is both even and then odd. Delaying a signal by t naught seconds does not change its amplitude spectrum, but the phase spectrum is changed by 2 pi f t naught. Okay. Note that the phase spectrum shifted changes linearly with the frequency f. Therefore, the time shifting property gives us this point to be noted. Delaying a signal by t naught seconds when compared to this, comparatively I am just speaking, t naught seconds does not change its amplitude spectrum, but the phase spectrum is changed. RE is real and IM is imaginary. So therefore, here you can have a real spectrum. Okay. Here you can have both. Two different colors are used for real is this one, and imaginary is this one. So therefore, note that the phase shift linearly with the frequency, whereas the amplitude spectrum does not change the amplitude spectrum, but the phase spectrum is changed by 2 pi f t naught. Time shifting property we can observe here. The next one is frequency shifting property, ft of e power j omega naught, f of omega minus omega naught, and is equal to f of omega plus omega naught, e power minus j omega naught and e power plus j omega naught. So frequency shifting property, often we use it in modulation, in frequency translation. Here itself I'll discuss about frequency. Frequency translation is nothing but changing the spectral representation of a signal without changing its inherent characteristics. We use the term modulation for frequency translation, like a particular characteristic feature of the information bearing signal is to be carried over long distance, so therefore there is every need for modulation. What do is we make use of this information bearing signal to be shifted by the high frequency carrier by using the property of frequency translation property or frequency shifting property of Fourier transform. We use to modulate the carrier. The carrier is being modulated by changing a particular parameter of the carrier in accordance with that of the information bearing signal, that is m of t. If you say m of t is the information bearing signal, c of t is the carrier, s of t as the modulated signal, then either but generally for any signal, the amplitude, the frequency and the phase are set to be the three characteristic features. We can change amplitude of the carrier in accordance with that of the modulating signal. We come out with AM by frequency translation. We can change the frequency of the carrier in accordance with that of the baseband signal. We come out with F frequency modulation. If we change the phase, similarly, we come out with phase modulated outcome. So therefore, we can have the low pass signal which is centered around DC. You can see here a low pass signal which will be centered around. In the next slide I can better show you. It is a low pass signal. You can see here whose spectral spread, you can see it is DC, from DC to a few hertz. on either side. To complete the spectrum, we also represent the negative frequencies, but in general, there is no negative frequency. To complete the continuous Fourier transform and its representation, we use in the entire representation of my 12 classes, we use the continuous Fourier spectrum also, right from we need to compute the Fourier transform right from minus infinity to plus infinity. So therefore, this is the best example of a low pass information bearing signal. We call it as a message signal. If this message signal is Fourier transformed, you can see how the frequencies are being presented. Basically, every message signal is a low pass signal. You can take it for granted as a thumb rule. Every information bearing signal is inherently low pass in its characteristics. So therefore, this low pass signal, as per the restrictions or limitations that are there in the low frequency signal transmission, we cannot transmit a low frequency signal over long distances. We cannot transmit a low frequency signal by using a physically realizable antenna. We cannot also propagate the low frequency signal over long distance against the unwanted noise and distortion which is always present in the channel. So normally when you transmit a signal into space, we use the space as the channel. And because of several different other limitations also, it's not possible for us to make this low frequency signal to be as it is transmitted. So therefore it's a non-transmittable signal, though it is an information bearing signal. If I want to transmit this information to some other long distant receiver, I need to make use of the frequency shifting property offered by Fourier transform. By frequency shifting, my baseband signal having a frequency of plus or minus b, maximum frequency you have b, its bandwidth is 2b. If I make the amplitude of my carrier, the internal sinusoid is called as carrier, whose amplitude is varying according to the amplitude variations of the original information bearing message signal. So therefore, the characteristics of the carrier is now varied in accordance with the variations of amplitudes of the information bearing signal. So here you can see the wherever the amplitude of the information bearing signal crosses 0, the phase of the carrier also change. This is a feature that we discuss in double sideband suppressed carrier AM. We'll discuss it at length in my third class. In the next class, I will discuss about conventional AM. So therefore, by using the previous property that we have seen, the property of frequency shifting by a particular frequency shifting which is useful in communication as we have done. So therefore, it is shifting it by plus or minus the same frequency of the high frequency component. Here the high frequency component, which is carrier cos omega cos 2 pi fct. I forget to mention, carrier frequency fc and the message signal frequency is b, let us suppose. So a condition, now you can clearly see that fc is much greater than that of b. The carrier frequency is far away from the DC, that is origin. Fc is a high frequency. So therefore, on frequency shifting this by using a convolution property or frequency shifting property, shifted around DC, the baseband signal which is present around DC is shifted to plus or minus Fc. This is the frequency shifting property offered by Fourier transform, because of which the modulation is a possibility. So therefore, you can see here the bandwidth that you have is 2b. Now the same bandwidth you can observe, but you will be, it is not present at DC. If I use a low pass filter, then definitely I can make it to be realized, but I need a band pass filter here in order to represent this. So therefore, free signal is being frequency shifted into a band pass signal. So the frequency shifting property of Fourier transform is used in order to modulate a signal. I'll define modulation as the process of converting a low frequency baseband signal into a transmittable band pass signal such that it suits the passband characteristics of the channel. Again, channel should also be a band pass channel. Now I can say that my low frequency signal is not centered at DC, it is centered at FC. So therefore, the new frequencies that the baseband signal assumes is FC plus B and FC minus B for positive frequencies, minus FC plus B minus FC minus B for negative frequencies. We call them as USB and LSB. In detail, we will discuss in the double sideband suppressed carrier modulation. So this is one very useful property of Fourier transform. We can say that multiplication of signal g of t by cos 2 pi fct places g of f centered at plus or minus fc. So therefore, the frequency shifting of the baseband signal or low pass signal happens here, which is a clear usefulness of the very useful and important property of Fourier transform. We can call it as frequency shifting property, or otherwise in communication terms we call it as the modulation property of Fourier transform. Modulation also comes from the frequency shifting property. For a modulated signal, you can see here an audio tone, which is a low pass signal, and the sinusoidal carrier, which is a high pass signal or a high frequency signal. A low pass signal and a high pass signal using the same frequency shifting property, we can have a carrier that is presented which is not that visible, centered around 500 Hz. We have a conventional AM wave, that is AM wave with full carrier. The envelope is carrying the amplitude. The carrier wave you can see here. Carrier waves amplitude is changed. The envelope, if you can observe, the envelope is varying as that of the amplitude variations of the message. That's why it is amplitude modulated wave. So frequency shifting property of Fourier transform can be used for generating an AM wave. The sixth property is symmetry. The duality property of Fourier transform, f of t is 2 pi f minus omega. You can see here the significance of the symmetry property. We can have a function g1 of t and another function g2 of t whose duality property we can just observe. g1 of f and g2 of f, a sinc function and a gating function. Time differentiation property also you can see here. The eft of dft by dt j omega f of omega. Frequency differentiation property also we can see here. The frequency differentiation property and the time differentiation property of Fourier transform. For unit impulse response, the impulse response of LTI systems also, we use the convolution definition of two functions f1 of 2 and f2 of t, and the convolved outcome of these two will be the response of the LTI system. You can see here f of t is integral minus infinity to f1 of tau f2 of t minus tau d tau is the convolution of the two time domain signals f1 of t and f2 of t. Here you can see here the convolution property is being better explained here also. The convolution of two signals f1 of t and f2 of t is equal to f2 of t convolved with f1 of t. So similarly, I can use the property which is properly represented here. The convolution property is quite useful for of the Fourier transform. You can have the following two systems. So if they are identical, I can make the signal to be passed like the h1 of t, h2 of t and h3 of t. h2 of t first, h3 of t next, and h1 of t will generate the same. So f1 of t, f2 of t and f3 of t are convolved, generating the two convolved, and after that the third one. The property of convolution continues, and a delta function, the convolution carried out with delta function will come out with the same function. Okay, why? Because the delta function response is 1 for t equal to 0 and plus it is not present. The next property, convolution property, we can see here. The convolution property of Fourier transform can also be used for a delayed delta t minus t. If I convolve, I'll get a f of t minus t. Okay, you can see here delta t minus t. Delta t is not represented here, of course. Shifted. Convolution property continued. F1 of t and f2 of t, f1 of omega. So the we can say that the convolution in time domain leads to the multiplication of their Fourier transforms in frequency domain, f1 of omega and f2 of omega. So the convolution property is also used for frequency convolution, as we have seen. And we'll also do a numerical here for cosine and sine in the next slides to come. f1 of t, f2 1 by 2 pi, f1 of j omega, f2 of j omega. Convolution frequency domain leads to multiplication in time domain. So the Parseval's energy theorem states that the signal energies of an energy signal and its Fourier transform are equal. The signal energy of an energy signal, this is the general definition of energy. Energy of a signal and its Fourier transform both are 1 by 2 pi integral f omega square d omega, which also computes the energy. That is why we can state that according to Parseval's postulated theorem of Parseval's energy theorem, it states that the signal energies of an energy signal and its Fourier transform are equal. With Parseval's property, we stop the properties of convolution as well the properties of Fourier transform, and we summarize Fourier transform of some use by looking into useful functions in time domain and the representation in frequency domain. Quickly we can go through for the unit impulse. This is the time domain representation and this is the frequency domain equivalent. For a single-sided real exponential, e power minus at u of t 1 by a plus j omega. For a double-sided real exponential, e power minus a mod t 2a by a square plus omega. Complex exponential function can be represented in frequency domain. The constant amplitude in frequency domain. The signum function, which is very important for us, even in the generation of Hilbert transform. We also on 90-degree phase shifting, we make the signal to be undergone through the signum variance that we will see in the generation of SSB signal for the signal function, which is 1 for t positive and minus 1 for t negative. That is, when t greater than 0 it is positive, plus 1, and t less than 0 it is minus 1. 2 by j omega is the corresponding frequency domain, that is the Fourier transform. For the unit step, we can observe from this slide the time domain and the frequency domain representation. The rectangular pulse, which we call it as a gating pulse. For that also you can see the time and frequency domain representations, and for a triangular pulse also we can see the time domain and frequency domain representation of the time domain triangular pulse. How we can represent it in frequency domain. The cosine wave cos omega naught t, whose Fourier transform, that is in frequency domain pi delta omega minus omega naught plus delta omega plus omega naught. For these two functions, we'll do the Fourier transform in detail for a sine wave. Why? Because we most generally we make use of these two functions for the generation of modulated signals. We generally use cos omega naught t and sin omega naught t. Sin omega naught t, the frequency domain represents j minus j pi delta omega minus omega naught minus delta omega plus omega. You can see here the problem. If you compute the Fourier transform of cos omega naught t, if I take cos omega naught t and substituting as cos omega naught t is e power minus j omega naught t plus e power plus j omega naught t by 2. So therefore, on taking this as the function, e power j omega naught t plus e power minus j omega naught t by 2 is cos omega naught. So that 2 we have taken it out. E power minus j omega naught t is the Fourier kernel or the basis function. Whatever the function that is being given, that function times the kernel. So we come out with the multiplication of these two. We come out with two terms, e power minus j times omega minus omega naught plus e power minus j times omega plus omega naught t. So which can be represented as pi delta omega minus omega naught plus pi delta omega plus omega naught, which we can see here. We have pi delta omega minus omega naught pi delta omega plus omega naught. The corresponding representation also you can see here, f of omega plus omega naught for positive frequencies minus omega naught. As we have computed, we are computing the Fourier transform in continuous domain. We need to take the integrating limits as minus infinity to infinity, and in fact this base should also be drawn darker. An impulse that is obtained at minus omega naught with an amplitude pi. This is the spectral amplitude. Similarly, darker line, nothing is obtained at DC, and again the darker line should be continued up to this point, and the spectral amplitude at omega naught for this impulse, the amplitude, spectral amplitude is, we should not clearly state that it is 1, it is pi. So therefore pi is omega minus omega naught and omega plus omega, omega minus of minus omega naught plus omega naught, omega minus of minus omega naught. This is the representation in spectral domain. So therefore for a cosine, so that is the reason why we can say that this spectrum is real, whereas for the next similar function, a sine function, you can see here, same Fourier transform of sine omega naught t, we have computed it. A sine function can be represented as e power j omega naught t minus e power minus j omega naught t by 2j. So therefore it is taken out, 2j is taken out. So the same procedure that we have carried out, this j multiplying and divide by j, we can get it as j square minus 1. The numerator j will be likewise minus j will be always present, and pi is always j, and j is the new quantity we will get for minus j times pi delta omega minus omega naught and plus j pi delta omega plus omega naught. So therefore minus j pi and plus j pi are the two spectral amplitudes of the positive frequency minus j pi delta omega minus bracket plus omega naught. That's why plus omega naught is represented here. Similarly, j pi delta omega minus of minus omega naught, that is the negative frequency. So therefore the magnitude spectrum of the Fourier transform of a sine omega t is complex. You can see minus j pi is the spectral amplitude of the positive frequency, plus j pi is the spectral amplitude. So therefore we generally not prefer the sine omega naught t for our computational ease. For modulation, we generally prefer a cosinusoid instead of a sinusoid whose Fourier transform is non-real, whereas this is real. So therefore we generally make use of the Fourier transform to be computed easily. A real Fourier transform we have obtained. So therefore for modulating or for representing modulated and modulating and carrier, we generally use a sinusoid. Okay. So the first problem under a Fourier transform, please note it down. The Fourier transform of a real valued time signal has odd symmetry, even symmetry, conjugate symmetry, or no symmetry. It was given in a 96 gate examination for 1 mark. The solution is, if f of t is real function and f of j omega is real plus imaginary, f of minus j omega is f star j omega. So therefore the real part is even and the imaginary part is odd. A real part of minus j omega is real part of j omega. Imaginary part of minus j omega is minus of f Fourier j omega. For real value time signal, Fourier transform has conjugate symmetry. So therefore the answer is C. It offers, this is what we can say, that even odd symmetries are being offered for a real valued time signal as being f of t is a real function we have taken, and we have proved that it comprises of conjugate symmetry. So therefore C is the answer. The second problem, please note it down. A signal x of t has a Fourier transform x of omega. If x of t is a real and odd function of t, then x of omega is, the options are a real and even function of omega, an imaginary and odd function of omega, an imaginary and even function of omega, a real and odd function of omega. It was given in 99. Get it. The solution is, if f of t is real and even, f of omega is real. We know for even, f of t is f of minus t, f of omega is f of minus m. So therefore, for even functions, we can see here. For real valued even functions, real and even function is the question. Real and odd is the question. So therefore, for even functions, we have verified. Even and real, f of minus omega is f star omega, or f of omega is f star omega. This is for even real. If f of t is real and odd, f of omega is pure imaginary, f of omega is imaginary, not real. And for odd, f of t is minus f of minus t, f of omega is minus f of minus. Okay, real and even, it is not a problem. If it is real and odd, it exhibits pure imaginary and even function. It's an even function. So therefore, the option B is correct. A signal x of t has a Fourier transform x of omega. If x of t is real and odd, then x of omega is an imaginary and even function is the answer. The next question is, note down. If g of f represents the Fourier transform of a signal g of t, which is real and odd symmetric in nature, in time, then A, g of f is complex, g of f is imaginary, g of f is real, g of f is, and the C and D options both are same, but the answer lies with something else. If g of t is real and even, g of f is also real, but if g of t is real and odd, g of f is imaginary. So therefore, the answer is B. The options C and D are same, but it is to be changed. So if a function which is real and odd symmetric in time, then the Fourier transform is imaginary. The next problem is, note down, the amplitude spectrum of a Gaussian pulse is A, uniform, B, a sine function, C, a Gaussian function, D, an impulse function. It is given in 98 gate examination, and the solution is a Gaussian function. We can say it is defined by f of t is equal to e power minus pi t square, which is a clear representation of a Gaussian function on Fourier transform of, on Fourier transform of this pulse. We can evaluate the Fourier transform f of e power minus pi t square integral minus infinity to infinity e power minus pi t square into e power j omega t dt. After evaluation of the integration, we come out with e power j e power pi f square. So therefore, the Fourier transform of e power minus pi t square is e power minus j pi square. So therefore, the Fourier transform also is a Gaussian. So therefore, the amplitude spectrum of a Gaussian pulse is Gaussian. Is the signal f of t. Energy of the signal f of t and energy of the signal f of 2t. If you keep on making the signal, you can see here in spatial or time domain, if you increment this in the frequency domain or in the spectral domain, it is diminished by some amount. E by 2 is the note to be made. Now I'll introduce a new transform. In addition to Fourier transform, we will also make use of a new transform, Fourier, Laplace and the Hilbert transform, which as I told you earlier, the Hilbert transform we have so far what is that we have discussed is we have seen few signals, the continuous time and discrete time signal representations, and the spectral representations, and we have seen the Dirichlet conditions to deal with periodic and aperiodic signals. We have seen the usefulness with Fourier series. We have done few numericals on Fourier series, and I just summarize what is that we have discussed in the last 1.5 hours. And the Fourier transform we have proposed for representing aperiodic signals as a sum of sines and cosines, and we have very clearly discussed the scaling and the translation, which is used for compressing. Scaling is used for compressing and zooming or expanding. The frequency translation property is used for modulation or frequency shifting or frequency translation. Okay, so and later we have done few numericals on Fourier transform. Now, whatever the next transform that we will use in the analog communication study is another transform. Another useful transform is Hilbert transform. We make use of Hilbert transform for the generation of 90-degree phase shifted signals. Why? Because to phase shift a signal by 180 degrees, there is a readily available ideal transformer is there. But for the phase shifting of 90 degrees, we cannot use a transformer. So therefore, there is every need to phase shift a signal by plus or minus 90 degrees in order to generate a single sideband suppressed carrier modulated signal. So therefore, I thought of introducing Hilbert transform in the introductory class itself. Later in depth we will discuss while we are discussing about the suppressed carrier modulation mechanisms. Fourier and Laplace domains and jet transform changes from time domain representation of the signal to the frequency domain representation. Not always we have to say that it is frequency domain. Fourier is frequency domain, Laplace is Laplace domain, jet is jet transform domain. The resulting two signals are equivalent representations of the same signal in terms of the time and frequency. In contrast to that, the Hilbert transform doesn't. We haven't discussed about Laplace and jet transform. I'm speaking about Fourier. The Fourier representation time versus frequency. In contrast to that, the Hilbert transform does not involve a change of time, a change of domain, unlike many other transforms. Strictly speaking, the Hilbert transform is, we say that it's not a total transform in its sense, and we again conclude that it is a transform. I'll tell you while discussing about it clearly. As we have changed the shape of the signal or phase of the signal in the Hilbert space, I can call it as, instead of transform, I want to call it as Hilbert space. First, the result of Hilbert spaced signal is not equivalent to the original signal. This is the clear-cut difference, rather it is completely different signal. The second strict difference between the Fourier analysis, that is what we have, especially the Fourier transform. The Hilbert transform does not involve a domain change. That is, the Hilbert transform of x of t is another signal denoted by the same domain in time domain. We have not changed the domain, we have changed the space from, let us suppose the phase of the signal is 0 in the original x of t. The phase of the signal on Hilbert transformation phase space, in the Hilbert space, it assumes plus or minus 90 degrees. So therefore, Hilbert transform of a signal is generally represented as cap. X of t is represented as x cap t. X of t is the Hilbert transform of a signal. Then x cap t, whose frequency component lag the frequency component. Lag means by 90 degrees. It shows some delay. X cap t, which is the Fourier transformed version of x of t, has exactly the same frequency components present in x of t with the same amplitude, except there is a 90 degree phase delay. Amplitude doesn't change, but the phase is delayed by 90 degrees on Hilbert transformation. Or when you change a signal from the space x of t to Hilbert space, it is delayed by 90 degrees. The Hilbert transform of x of t of a cos 2 pi f naught t theta is, you can see here, a cos 2 pi f naught t plus theta minus 90 degrees, as cos 90 minus theta is sin theta, so you can call it as a sin 2 pi 2 pi f naught t plus. So therefore, when I am interested in obtaining a sinusoid from cosines of minus j signum f is the ultimate solution to the Hilbert transformed signal. So Fourier transform of the signal is multiplied by minus j signum f. You will come out with the Hilbert transform version of the signal. So now assume x of t is real and has no DC component. So I can compute the Fourier transform of x cap t. What is x cap t? X cap t is the Fourier Hilbert transformed signal x of t, which is phase lagged by 90 degrees. So if it is cos 2 pi f naught t, it will be sin 2 pi f naught t. That is cos 2 pi f naught t plus theta minus 90 degrees is the actual signal. Now, if I take the Fourier transform of the Hilbert transformed signal, as I told you, is minus j signum f is to be used to for Fourier transform minus say j signum f x of f. So therefore, the inverse Fourier transform, if I compute, f inverse of minus j signum f is equal to 1 by pi t. So therefore, 1 by pi t times x of t is the desired signal, which is the Hilbert transformed signal. 1 by pi t convolved with x of t will be 1 by pi integral minus infinity to infinity x of tau divided by t minus tau d tau is the definition of the Hilbert transform. So therefore, x cap t, the Hilbert transform of x of t is defined as 1 by pi t convolved with x of t, that is 1 by pi integral minus infinity to plus infinity x of tau by t minus tau d tau. The operator of Hilbert transform is equivalent to a convolution, that is filtering. So this is the actual definition of Hilbert transform. In a reverse order, we have developed this formulation. The concluding remarks on Hilbert transform is by performing the Hilbert transform on a signal is equivalent to a 90 degrees phase shift in all its frequency component is the first observation. Therefore, the only change that the Hilbert transform performs on a signal is changing its phase. The amplitude of the frequency component of a signal do not change by performing the Hilbert transform. On the other hand, since performing Hilbert transform changes cosines into sines, the Hilbert transform of x cap t of a signal x of t is orthogonal to x of t, which is orthogonal. Why? Because a phase change of 90 degrees took place, which is lagging. Also, so therefore, on performing the Hilbert transform, which changes sines into cosines, or the Hilbert transform of x cap, which is the x of t's Hilbert transform, is orthogonal to x cap t is orthogonal to x of t. Since the Hilbert transform introduces 90 degree phase shift, carrying it out twice causes 180 degrees phase shift, which can cause a sign reversal of the original signal, which is very clear. Now we can see a few properties of the Hilbert transform. The first property of the same spectrum we will get the signal x of t and its Hilbert transform x of t will have the four properties. If x of t and x of minus t, if x of t is equal to x of minus t, then the Hilbert transform is minus x cap of minus t. If x of t is minus x of minus t, then even and odd, then x cap t is equal to x cap minus t. If x of t is cos omega naught t, we obtained it sin omega naught t. If it is sin omega naught t, we obtained it as minus sin omega naught t. X double cap means 2 times the Hilbert transform of a signal is minus x of t. Integral minus infinity to infinity x square t dt is equal to integral minus infinity to infinity x cap square t, means its Hilbert transform also results in same. Similarly, x of t and its Hilbert transform, why? Because both are orthogonal, so therefore it results in a 0. A signal x of t and its Hilbert transform x of t will have the same amplitude spectrum, the same autocorrelation, and x of t and x cap t are orthogonal, and the Hilbert transform of x cap t is minus x of t is x cap t. So this is about Hilbert transform. Again, I am just repeating. We'll see its applicability in developing the suppressed single sideband modulated equation, modulated signal equation, as well the band pass signal generation. Now I'll move on to the general diagram of an electrical communication system. Now I'll stop my signal introduction. We have seen the brief introduction to signals and brief study on Fourier analysis like Fourier series and Fourier transform. And as we make use of Hilbert transform, we have also spent some time on the study of Hilbert transform. Now we will see a realistic electrical communication system. An electrical communication system comprises of basically a, a, a communication system comprises of a source and a destination separated by input and output transducer. Transducer is a device which converts one form of energy into another form of energy. We can say that this functional block can be considered as a transmitter where the source signal is originated. The originating place is transmitting center. The source signal is made to be transmitted here by using a transmitting antenna here, and we can make use of a communication system for transmission of the source that is converted into one form of energy is converted into another form, that is an input signal which can be communicable signal. To make it a communicable signal, we make use of a transducer. We make use of a communication system to transmit it through the communication system. The output of a communication system is taken by the output transducer. So therefore, whatever the way, normally it's not an electrical signal. Source may be a voice, an image, as we have seen, 1D, 2D or 3D signal, a video that is to be converted properly by the input transducer into a signal which can be properly connected to the communication system. Communication system doesn't take speech as it is, images as it is, or videos as it is. They are to be converted into any equivalent electrical signals. Those electrical signals can be fed to the communication system. That is the actual input. Electrical input is given to the communication system. Electrical output is the output of the communication system. Now, the destination is the receiver, source at a transmitter. The receiver doesn't understand electrical signals, so therefore the output transducer's duty is to convert back the electrical signal back to the original. If it is speech, the electrical signal is to be converted into speech, delivered in the receiver, to be delivered and observed by the destination device or seen in the destination. And if it is an image, that is to be down converted by the output transducer. So therefore, what is that we are doing is a raw signal is electrically converted into a communicable signal by an input transducer. The communication system transmits that signal, and this electrical signal, which is the output of the communication system, is again down converted to the original signal by the output transducer. So the input and output transducer takes the source information. Detailed diagram of the electrical communication system in the bottom line. It is a raw communication system block diagram. A detailed diagram you can see here. It comprises of the communication system comprises of a transmitter, channel, and receiver. These three comprise of a communication system. In addition to this, unavoidable noise will be included. These four comprise of the communication system, the input transducer, and the information source. Sound, picture, speech, or any data is the information source. Input transducer is converting this information into electrical form that will be given to the transmitter, which makes of a transmitting antenna that will be generating it to the channel. Every signal will be passing through the channel, which is the key point where unwanted noise will be included or induced or added to the signal. So we often, in analog communication study, we always consider the additive noise component. We don't consider any multiplicative noise component. It doesn't mean that there is no multiplicative noise component. There are multiplicative noise. For analog communication study, we restrict ourselves for the additive noise components only. So the noise components, that are added to the transmitted part of the signal and will be readily available at the input of the receiver. The function of the receiver is to faithfully reproduce all the source information received in electrical form. Now the electrical signal is to be converted back to its original form. If it is a sound, it is to be converted into the sound. If it is a picture, it is to be converted. That is being carried out by the output transducer. That output transducer gives the original signal. This is how a communication system works. The source information is converted into equivalent electrical into the transmittable signal through the channel, where some added noise is also added with the original signal. The noise added signal is received. How best your output transducer or the receiver is capable of minimizing the noise. I am not saying that it is totally nullified. The objective of the receiver is to faithfully reproduce all the information that is being transmitted by the transmitter, but the receiver's capacity at times is enough for delivering the information to the fullest extent. If noise dominates the signal, then some amount of the signal, only some part of the original signal we will receive. So therefore, information is being received through a communication system like this. So here itself we can say that transmitter is a point where modulation is carried out. The receiver is the point where demodulation is being carried out. So therefore, we make the low pass information bearing signal into a band pass transmittable signal by a process called modulation. Leave about the electrical conversion by the transducer. So now you have a low pass signal converted. If you take any of these 1D, 2D or 3D signal, originally they are low pass. By using a process called frequency translation or modulation, we make it a transmittable signal, makes it a band pass. So a band pass transmittable signal will be passed through the channel. What kind of characteristics does the channel should possess? So the channel should possess band pass characteristics. That is the reason why I have defined modulation as the process of converting the low frequency baseband signal into a transmittable band pass signal such that it suits the passband characteristics of the channel. If it suits the passband characteristics of the channel, the entire transmitted signal will be received here. Leave about the effects of noise. Will deal with the effects of noise differently. Will deal with the effects of noise differently on receiving the signal. We'll also discuss about the effects of noise in a separate class under noise heading. If AM signal is transmitted, what is the received signal capacity? We call it we measure it in terms of figure of merit. If an angle modulated signal is transmitted, what will be the figure of merit? And we will compare the figure of merit of different modulated signals that are received, and we will come out with a conclusion that what kind of a signal modulation gives good figure of merit or acceptable figure of merit. Then we will conclude a particular modulating mechanism is proper and adaptable. So therefore, a band pass signal is transmitted through the channel, and receiver also receives the transmitted signal in its band pass characteristics. And as I told you, demodulation is being carried out. So inverse process, the band pass signal is again being converted into a low pass signal. So therefore, how best we can make it to be proportional to the original information bearing signal is the function of the receiver. Not all the function of the receiver is only to detect. Receiver also performs so many other activities that are unwantedly induced to the signal in the channel. We have several different building blocks that are there for the receiver, and one such building block prior to the delivery through the output transducer, if it is a loudspeaker, we need to properly down demodulate and then make that low pass signal to be delivered properly through a delivery device. Delivery device may be loudspeaker or the mobile scanner, whatever it is. All the output devices, we can take them as received signals. So that is how a communication system works. Modulation is carried out. The information bearing signal is converted from low pass to band pass, and the band pass signal received and down converted into low pass into a an understandable information. That's how the communication system works. Now, for a few minutes, I will discuss about the need for modulation. The purpose of every communication system is to uh, transmit the information bearing signal or the original baseband signal through a channel, as we have seen, separating the transmitter from physically. The transmitter is widely separated from the receiver. So therefore, the baseband signal, which is a low pass signal, used to represent the band of frequencies in the original signal as delivered by the source of information. So therefore, communication channel requires a shift of range of baseband frequencies into other frequencies ranges suitable for transmission and corresponding shift back to the original frequency range on reception, after reception. To see to that, I'll tell you one example that majority of the radio systems works on a frequency. We can say that it works about 30 kilohertz and above. And whereas the baseband signal, if you take the human voice audio frequency, most of the male voice falls at about 3.5 to 3.8, and female a little more. So therefore, if I want to take my baseband signal, which is in the order of 3 to 3.5 kilohertz, in a radio system whose operating frequency is in 30 kilohertz, here itself we can come to a point of frequency band shifting. So there is a need for frequency band shifting. So therefore, for satisfactory operating of the system, a radio system, we need to change the shift of frequency. We need to convert the frequency of the low pass signal, which is, for example, an audio, into a radio frequency which is in the order of 30 kilohertz and beyond. So therefore, a shift of range of frequencies in a signal is accomplished by a process. What we call that process as modulation. Modulation is the process of shifting the range of frequencies of the information bearing baseband signal. So therefore, modulation is very much essential. So modulation is required for several different reasons. Modulation is desired for multiplexing different messages bearing signal in different frequency ranges. Multiplexing means several different messages can be transmitted through the common communication channel without mutual interference. Suppose 4 or 5 people are speaking over the channel in a mobile channel. More than a plurality number of messages are coming, and all these messages need to be delivered through the destination without interference from one signal to the other signal. So therefore, there is every need for modulation. Modulation enables multiplexing. So modulation makes it possible for the physical size of the transmitting antenna or receiving antenna to assume a practical value. Antenna size is directly dependent on the wavelength, we all know, are inversely proportional to the frequency. A high frequency equal to f lambda, we know C is equal to f lambda is the equation. So therefore, as lambda is equal to C by f, which is the denominator part of it. If the denominator part is more, means the frequency of the signal is more, lambda will be less. Lambda by 4 is the minimum size of the antenna, quarter wave antenna, if you can say. Lambda by 4 will be minimized as we can increase f. So therefore, higher and higher frequency conversion of the baseband signal is very much required. So therefore, practicability of antenna is also a feasibility if you increase the frequency of the signal by frequency translation. So therefore, a higher frequency range gives lower antenna size, and lower frequency gives a higher antenna size. So with the frequency domain conversion of the signal into a low frequency into a high frequency will definitely make the physical realizability of the antenna. Modulation is also used to shift the spectral component of a message signal so that it lies inside the operating frequency band of the communication channel, which converts the signal to a relatively narrow band. The signal is a wideband signal, which will be converting this into a relatively narrow band signal, and solves many implementation issues for shifting of the signal to a common frequency range to the use by same processing block. Modulation is used to shift the spectral content it is used to shift the spectral content of a message signal so that it lies inside the operating frequency band of the communication channel. Most of the communication channels are band pass. So therefore, it converts the wideband signal into an narrowband signal, and thereby other same processing blocks may be used. Modulation provides a mechanism for putting the information content of a message signal into a form that may be less vulnerable to noise or interference. So therefore, we need to take care of the noise and interference problems that may be seen in when the signal is modulated and transmitted to the channel. There is an additive noise that is added with the transmitted signal. So therefore, we need to take care of those unwanted problems because of the modulation. So therefore, modulation is required for multiplexing. Modulation is required for physical realizability of the antenna by converting the low pass signal into a high frequency signal by frequency translation. Modulation is used to shift the spectral content of the message signal so that it lies inside the operating frequency range band of the channel, and modulation also provides a mechanism for the information content which is transmitted will be less vulnerable to the noise or interference. So therefore, there is need for modulation. We'll see in the next class how we can modulate the signal and how we can get the modulated version of the signal, which by using a process called frequency translation or modulation. For all my presentation for signals and systems, I have used Simon Hyken and T.K. Rawat part, and I am using communication systems by Simon Hyken. These are my references, and which are useful standard books on communication. Taub and Schilling and Gautam Saha also I am using. Modern Digital and Analog Communication by B.P. Letty and the co-authors I am also using. And for noise and receivers chapter, I am relying on Electronic Communication Systems by Kennedy and Davis. And for signal systems, so we make use of T.K. Rawat as well. Signal systems by Simon Hyken also I am using. So in the next class, we will thank you very much for patient listening for about 2 hours of my lecture. I would like to start the session by the same time tomorrow, and we will fresh start the process of modulation and frequency translation. Thank you very much for listening to my class. Thank you very much. My class is over. Thank you very much. If you have any questions, please send them through the Google form. I will try to answer all the questions in the beginning of the next class. In the while we start the next class, I will try to answer all the questions posed by students, the audience. Thank you very much. సార్ క్లాస్ అయిపోయింది సార్ చేయండి సార్